So hi all, welcome to the next GOAT seminar. Today we have Dennis Bulavka from Charles University, and he'll talk about Erdős-Ko-Rado for simplicial complexes.
Thank you very much. Thank you for inviting me. This was a very nice surprise. So I will be talking about the generalization of this Erdős-Ko-Rado for simplicial complexes. Usually it's for set families, but for us, we will be looking at simplicial complexes. So all what I will say today is a joint work with Russ Woodruff from University of Primorska. So let me just start with the classical theorem of Erdős-Ko-Rado. Maybe you've heard of it. It's about bounding, upper bounding, the size of a pairwise intersecting family, right? So we have a ground set of size n. You can think of it as n vertices, and we take subset of size r. So the size r is fixed. So we take a bunch of these subset of size r, and the condition of the family is that every two elements will intersect. So every two families intersect. And so, for example, you can think of you fix one element, and then all the rest contain this fixed one element. So you have n is your ground set, and since each of these must have size r and one element is predetermined, you have r minus one choices. So for example, this intersecting family has size n minus one, choose r minus one. And what Erdős-Ko and Rado show is that this is like the maximal thing you can achieve. Like you fix one element and you take all the R sets that contain this element. And I will usually say that this type of families are the trivial families. Frankl says trivial, some people say canonical. I'm sorry if that's confusing. So if you have a pairwise intersecting family, its size will be bounded by the trivial family. And moreover, if R is strictly less than number two, doesn't matter. If you have a family achieving this upper bound, it must be of this shape. So that is the statement. There are two parts. One is the upper bound, and the second part is the characterization of maximal families. So I said we will be talking about this in terms of simplicial complexes. So let me just say the definition. A simplicial complex is just a set family that is closed and are taking subsets, right? Like you have I'll make a drawing. Like if you have three vertices, 1, 2, 3, the simplicial complex, like you can represent it with a picture, but it's also the set 1, 2, 3, 1, 2, 1, 3, 2, 3, and 1, 2, 3. Right? So this will be an example of a simplicial complex. So if you have the sets of size 3, which we think of them geometrical triangles, and then the edges, and then the vertices. And we will need just two constructions. One construction. One is the link of a vertex. So the link of a vertex is the simplicial complex of faces that do not contain the vertex, but if you add the vertex, it's somebody in the simplicial complex. Element of the simplicial complex are called faces. So for example, here, the link of 1 is the simplicial complex given by this edge and these two vertices separately. So the link of 1 in this case is 2, 3, 2, 3, right? And I will denote Fr of K, the faces of size R, and I will say R face to when I say R face, I mean the face of size R. Usually people, when they say R face, they mean a face of size R plus 1, but I didn't want to put plus 1s everywhere or minus 1s, and this notation has been used before, so I blame those people. So what do I mean by Erdős-Ko-Rado for simplicial complexes? Well, let me just restate this this theorem. This is just a restatement in this new language. So we look at now our simplicial complex is the simplex. So we have all the subsets of a ground set of size n. So we have n vertices, we take all the subsets, that's the simplicial complex. We look at the pairwise intersecting family of R faces. So just a restatement of subset of size R, these are R faces. Then its size is bounded by the number of faces of size R minus 1 from the link of a vertex. So if we took in the simplex the link of a vertex, that's a simplex of just one size smaller, and then all the number of R minus 1 faces is just n minus 1, choose R minus 1. Yeah, so this is just like a translation. There is nothing new except that we use this new language in a sense. Any questions? Is it correct?
If you say some vertex, does it hold for every vertex?
Yes. So here it's not for every that there exists some vertex. Sorry, there exists some vertex that is upper bound. Yeah. Good question. Like in the case of the simplex, it's not important, but in the general case, it is important. Yes. You want that there exists a vertex, and that usually is the one that maximizes. Because you can always pick a vertex and take all the faces that contain it, and that will be an intersecting family of size R minus 1 of the link. Yeah. So in this suggestive reformulation, somehow the question we want to ask is we would like to remove this 2 to the n, right? We would like just to ask it for any simplicial complex. Like I take a pairwise intersecting family of R faces in a simplicial complex. Is it true that I can upper bound it by the size of a link of a vertex? Yeah. So this is this is a very strong question. We weren't the first to think about it. So it was suggested in 2005 by Holroyd and Talbot. They were looking at a specific type of of simplicial complexes that I would say in a little bit. But Borg asked this question for simplicial complexes in general with the translation. So I will just go back to the previous slide. There is this. Now I'll just say something about this R to the that R is at most n over 2. This condition, before it was on the number of vertices, but it translates to R can be at most the smallest facet. So you remember faces are elements of the simplicial complex, and facets are maximal faces. Okay? So among the maximal faces, you pick the smallest one. That is your D. Okay? And if R is at most the size of the smallest facet divided by 2, then they conjecture that a statement of the same as before must hold. So the first part of this conjecture is called like that. They say that the simplicial complex satisfies the EKR property or R EKR, and the second part, the characterization, is the strict R EKR property. There has been some evidence towards this conjecture. As I said, when they started studying this conjecture, it wasn't for simplicial complexes, but it was for the independence complex of a graph. So the independence complex of a graph, given a graph, the independence complex has vertices, the vertices of the graph, and the faces are independent. Set of vertices that are an independent set. And it is closed on the taking subsets, right? Like if you have an independent set, take a subset, it's an independent set. So for this type of simplicial complexes, Hurberg and Kamat said that if you have a chordal graph with an isolated vertex, then so if you have a vertex V and a chordal graph, and you take the independence complex of it, and D is the smallest facet cardinality of this simplicial complex, then for any pairwise intersecting family, its size will be bounded by the link of this disjoint vertex. So for chordal graphs with an isolated vertex, this conjecture holds. The first part, this upper bound. There were other constructions, Holroyd, Spencer, and Talbot. Basically, what they did is take large disjoint unions of clique, bipartite graph, complete bipartite graph paths, cycles, and if you have enough of them, you can conclude the same upper bound, basically. But there is a result for general simplicial complexes, and this was the work of Borg in 2009. That basically his result is if your minimum facet cardinality is large enough. So in this conjecture, it's asked for that R is at most D over 2, but in here is like you fix R and D must be at least big O of R cube, basically. Like if D is big O of R cube, then the conjecture holds both parts. He showed this. If this is true, like both parts of the conjecture hold, the characterization and the upper bound. On totally different, like not the general case, but and not the combinatorial characterization in a sense, but Ras Woodruff showed for simplicial complexes that are, I would say, nice. This is a topological condition, but it turns out that this class of nice simplicial complexes is big. In particular, it includes chordal graph with an isolated vertices. So Ras showed that for this class of nice simplicial complexes, the upper bound holds. Yeah. So it was open until we solved it. If the second part was also true for this class of nice simplicial complexes, and in particular, so that's the result. In particular, it shows that the second part of the conjecture is true for the independence complex of a chordal graph with an isolated vertex. So if you have a maximal family, if you have an intersecting family achieving the maximal size, it must be that family containing the vertex V. So it's one of those. I mean, the Erdős-Ko-Rado theorem is one of those theorems that it happens what you expect. There is no big surprise there. Although this conjecture it is pretty surprising if it holds. Yeah, and maybe just to mention a couple of more graphs that are in this class. Well, apart from chordal graphs, there are also graphs with no index cycle of length other than 3 and 5, and there is some other maybe coming from topology, incomparability graph of shallable posets, and some graphs coming from geometry. But I just to illustrate that there are more simplicial complexes here. Okay, so yeah, that is a statement. Is it clear? Not somehow what we want to do. Say, okay, how do we do it? And basically, there is this approach. I mean, the original approach of Erdős-Ko-Rado was about compressing your intersecting family and then assume and compressing makes it simpler, and then showing it for the simpler one. And this is a bit what we do. One part of what we do, there is a compressing operation called shifting or combinatorial shifting. And basically the idea is to, in your family, replace higher vertices with lower vertices. So if you have vertex 2, you would like to replace, when you can, with vertex 1. Okay? So maybe I'll do an example. Like if you have 1, 2, 4, you would like to replace 4 with 3, so you end up with 1, 2, 3, and somehow 1, 2, 3 is simpler than 1, 2, 4. And you can apply it to you apply this operation with respect to with respect to a set family, and you want to take into account, you want to preserve certain properties. One is that the size of your family doesn't change, and the other thing is that the size of the elements in your family don't change. Like if you have R sets, you want to keep R sets, and you want to also preserve the cardinality of your set family. And these are basically the conditions you have to ask for. Like if you have J and I in your set, you don't want to exchange J with I because that would make the set smaller. And if you did the exchange, you don't want it already be in the family because then you will reduce the size of the whole family. And it turns out that if you do this on the whole on your whole family, this preserves the pairwise intersecting property. So if you have a pairwise intersecting family, you apply this combinatorial shifting, you again have a pairwise intersecting family. And then what you do is you can just assume that you have a shifted. So a family is shifted if it is invariant under this operation. So if you try to exchange J by I and it doesn't change your family, then it is shifted. Shifted families are nice because Borg showed in his article that if your simplicial complex is shifted, then the conjecture is true, both parts. And so then one could ask, okay, why don't you just apply this combinatorial shifting to your simplicial complex and your family at the same time until you end up with the shifted simplicial complex? But it could break the minimum facet cardinality. So one has to be very careful how to do this. So our idea is to transform our nice case somehow with another shifting operation into the shifted case, and then apply this result by Borg. And what is this other type of shifting? It's type of shifting introduced by Bulavka. It's called zero algebraic shifting. I won't give the definition, but I will just say some properties, and that's what we need. Basically, what it does is when you are given a simplicial complex and you apply this magical operator, you end up with a simplicial complex. It preserves the number of R faces. It preserves inclusion. It preserves the pairwise intersecting property. And if your simplicial complex is nice, so Cohen-Macaulay or sequentially Cohen-Macaulay, then the shifted, then after you apply this, you have something shifted, but also has the same minimal facet cardinality. So the size of the minimal facet is the same. So at this point, without paying attention to what is under 5, you might think of, okay, so you have your pairwise intersecting family. You can apply this magic operator. You end up with something. You end up with something that is shifted, and it's a shifted simplicial complex. It has the same minimum facet cardinality, and now you can apply Borg's result. Well, not quite, because we are interested in this characterization part, and in the characterization part, it's important that to show it that if you start with something that is not of this shape, it's like meaning that it is not trivial, like all the things don't intersect. So we would like to show that this shifted family is also of this shape, is also not non-trivial. So what could happen is that the intersection of all the elements in F is empty, but the intersection of all the elements after the shifting is not empty. And to illustrate that, I just have an example here of if we have a tree and we apply this magical shifting, and you have to believe me, that you end up with a star. And just to illustrate that the edges of a tree don't have a common intersection, the edges of a star do. This is where the last condition plays for us a role, which is that it preserves the number of, let's say, linearly independent cycles in a graph, or or in higher dimensional simplicial complexity. And we can see with this example, if you have a cycle, then when you apply this operator, we end up with a cycle as well. And you can see that this cycle is a witness, in a sense, for not being trivial. Like if I intersect all these three edges, the intersection will be empty. Like there is no vertex contained. So this is kind of the background. And so how do we merge these two compressing techniques? What we want is to guarantee that there is this cycle in the pairwise intersecting family. So we cannot apply directly the algebraic shifting, but we will apply first the combinatorial shifting until we guarantee a cycle, and then we apply the algebraic shifting. That's basically the idea. So we start with a pairwise intersecting family that is not non-trivial. I mean, meaning that there is no common intersection, and we assume it is of maximus. Basically, we apply this combinatorial shifting with respect to this disjoint vertex. So we apply we try to compress as much as we can. If while it is not non-trivial, so we apply this combinatorial shifting. We apply this combinatorial shifting to the pairwise intersecting family iteratively, and if at some point it became trivial, we just step back and output that thing, whatever that is. If we never came to a stable family, if we never got to a trivial family, that means that our set system is stable, so I can exchange every vertex with V, and it will still be in the set family. So since it is non-trivial, there must exist some F that doesn't contain this V. But since I could exchange this any vertex of F with V, I actually have all the R sets of F union V. And if you replace R with 2, this is just the triangle. If you replace R with 3, it's a tetrahedron. Like F union V, choose R is the boundary of a simplex. So that's my cycle. And after this, I can apply the algebraic shifting, and I'm in the situation of Borg's result. And the other scenario is that this became trivial at some point, and there are two cases to analyze. One case is that there exists some R-1 set, such that if it became trivial at the shift VU, there are R-1 set F, such that FU and FV are in there, and I can again guarantee a cycle inside, and I can again apply the algebraic shifting, and in the condition of Borg, or let's say the hard part of the proof is that for each F of size R-1, either U union F is in the family or V union F is in the family. And since either one of them is there, I will define an injection. So this is the next slide. And basically, since I have either U union F or V union F in H, for every element in H, I can remove V or remove U if one of them is there. Okay? And this function is injective by this assumption that we are in this case, and we claim that it is not surjective. And the not surjective part is a bit technical, but basically what we do is we restrict the analysis to a facet, and a facet is just a simplex. Sorry. So a facet is just something of the shape 2 to the D, or some not necessarily D vertices, could be more. And in a facet, we know how things behave, and we use basically we build two cross-intersecting families, and we use the bound on cross-intersecting families to guarantee that there is something in the facet that it is not in the image. And this shows that it is not surjective. So we have a function that is injective but not surjective into the link. So its size must be strictly less than the link. So this is that's the idea. I have a little bit more of time. So this finishes the sketch of this proof. I would like to just present two more results related with this topic that we also obtain with trust. One is there is a Hilton-Milner theorem that is a stronger version of Erdős-Ko-Rado, like one could say this is a stability result. Basically, in the Erdős-Ko-Rado I stated in the beginning, if we have a non-trivial pairwise-intersecting family, we only have a strict inequality here without this last term, just a strict inequality there. But Hilton and Milner show that actually you can improve the inequality, and this inequality is tight. And to see that it is tight, you can consider the family that has as elements the set from 2 up to r plus 1. These are r vertices, and all the other elements contain vertex 1 and intersect 2 to 2 from this interval. All the other elements intersect this interval. And so these are all the things that contain 1 minus those things that contain 1 and don't intersect this interval plus this interval. So that's where, and we can restate it for simplicial complexes as before. So basically, we can upper bound it by the size of the link minus the size of the link that do not contain vertices from 2 up to r plus 1. And again, what we would like to replace this k by a simplicial complex. And so since we have this independence complex of a chordal graph union, this disjoint union vertices, is that enough? And what we found is that we need to ask for more disjoint vertices. So sorry, there should be d over 2. And basically, if we are looking at r faces, we need r plus 1 vertices. Disjoint union with a chordal graph, and r is at most d over 2, where this is the minimal fast cardinality, and we can give an upper bound on its sides. And the last thing I would like to share is that we also can bound the size of cross-intersecting families. I mentioned that we use cross-intersecting families in the last step. And basically, to set families at cross-intersecting, if picking each element from one family intersect each element from the other family. And Hilton and Milner show that we can upper bound the size or the sum of sizes, and this upper bound is also strict. Like basically, you take one of the families to be the interval of r elements, and all the other to be the elements intersecting this interval. And so here are all the R sets minus those R sets that do not intersect the interval R plus the interval R. And we can reformulate that the same, like all the R faces minus those R faces that do not intersect the first R vertices. And again, if we have enough disjoint vertices in a chordal graph, we can guarantee an upper bound on the sum of the sizes. Yeah. So, and just to say, like this, I mean, I state these results with GA chordal graph, but this holds for nice simplicial complexes. Nice enough. Yeah, they are nice for me. Yeah, so yeah, that's all. Yeah. No,
Any questions?
So I have one. You use as an example this nice simplicities, this independent set of this chordal graph with this single isolated vertex.
Yeah.
But then at some slide you had like chordal graphs in general. The sort of maybe go back. Previous one. Yeah. Yeah.
Yeah. There should all of these with an isolated vertex.
Oh, okay.
Yeah,
okay.
sorry. Yeah.
So it's not known to hold for.
It's not known to hold for chordal graphs by itself.
But the conjecture is that.
The conjecture is that it is.
Yeah.
Okay. So yeah, so that's a very good to show how little is known. It is not known for the independent complex of the chordal graph.
Thank you.
And somehow like this vertex is the one we are using to upper bound the size, and somehow in a general chordal graph, like it's hard to choose a candidate for the vertex.
Some more questions.
So you showed the proof for the case where the complex comes from the chordal graph plus the vertex, and you said that in fact it holds for some more general topological properties. So my question is, so maybe if you can elaborate a bit more about what the topological property is. And my question is whether the proof in the general case is still like combinatorial, or does it use?
So the proof. Let me just think. What is the best way to answer this? So basically, it proceeds as follow. Like there is this sequentially Cohen-Macaulay property, and that is that property allows you to justify that when you apply this magic shifting, the end result has the same minimal facet cardinality. That is, and the definition of sequentially Cohen-Macaulay is basically I'm going through a. Basically, you take a simplicial complex and you can take the pure skeleton, meaning that you take the faces of that dimension and you close under. You need you take so you take your simplicial complex and you take the pure K skeleton. And pure K skeleton meaning that the subcomplex that is pure and of dimension K, and you ask that each of these for each K is Cohen-Macaulay, and Cohen-Macaulay is some homological condition. Basically, like homology at every link is 0 except the top line. Basically, that things look like a sphere. That's kind of what you as good. But why we use this? Is because the minimal fast cardinality is preserved, and that is why. Yeah. And people show that these graphs are Cohen-Macaulay, and somehow we get for free these examples. Yeah. So yeah, I didn't give the definition of this magic shifting, but it involves some vector spaces, and it's not really clear the properties that they hold. Yeah.
I was just wondering, so all of these examples are independence complexes of some graphs.
Yeah.
So is there another example of how to get a complex that satisfies this Cohen-Macaulay?
You can take okay, there's I guess the easy way to answer that question is there is a combinatorial characterization called shellable simplicial complexes.
Okay.
And those are the ones that you kind of build by gluing along a codimension 1 thing. Like if you have if your dimension is 2, you can just glue them like this.
Yeah.
And so those would work. So yeah, shellable complexes would work. Because like shellable is stronger notion, but I guess that's it.
Okay, so if there are no more questions, then let's thank the speaker again.